So we'll start with the inaugural function for a AICTE sponsored 1 week online faculty development program on 3D printed composite material technologies and application. So we have a chief guest for the today's inaugural function, Dr. Prabhakar, Associate Professor in Department of Mechanical and Civil Engineering, University of Wisconsin-Madison, USA. So it's with great pleasure, respected chief guest, Dr. Prabhakar, Dr. Madhuri Khambete, Principal, Cummins College of Engineering for Women, faculty members, and my dear participant. It's give me immense pleasure to extend a warm, heartfelt welcome to all of you to a ATAL Online FDP on 3D printed composites, which is organized by Department of Mechanical Engineering, Cummins College of Engineering for Women. Today, we are gathered here to inaugurate this FDP. First and foremost, I would like to extend my gratitude and respect to our chief guest, Dr. Prabhakar, for gracing the occasion with their presence despite their busy schedule. I also take opportunity to acknowledge the presence of our principal, Dr. Madhuri Khambete ma'am, and sponsor of this FDP, AICTE-ATAL. To set the tone for today, let me briefly introduce our program. The theme of a program is 3D printed composites. So the use of composite material is started early 1960s and 70s. Specifically, main purpose of this composite material was initiated for aircraft structures. The good reason for starting the make use of composite for aircraft structure because of the weight reduction, which results in a greater fuel efficiency and the reduced emissions, rise to a lightweight solution for aircraft industry. But now in the today's era, composites are also used in automotive industry, construction, medical, energy, sports, and many more. So there is a high demand of the development of a new form of composites in this all the across the industries. The second advantage we have it with this of composite material is the tailored performance. As the need rises, according to the requirement of specific application, we could tailor the performance of composite material. So one of the keyword of our FDP is composite. The second interesting point about the is 3D printed composites. So 3D printing or additive manufacturing, which has enabling to fabricate intricate shape of the structure, which is not much possible or very much costly with the traditional methods of the manufacturing. And secondly, we also have a tailored product to be manufactured as per the request of the customer. So on-demand customization, the on-demand customization that is a possible scenario with 3D printing. So on base of this advantage of both of these technologies, additive manufacturing and composite material, we frame up a FDP on 3D printed composites. In context of 3D printed composite, we likely to have the sessions in context of materials, technologies, and applications. So in coming week, we have FDP. In coming week, we have an expert session through this FDP, which will take a prospect of materials. So we likely to get the expert session in the form of different materials. Like today, Professor Dr. Prabhakar likely to highlight architected sandwich foam composites. Similarly, we have a few sessions related to functional polymeric material, natural composite material, metal matrix composite material, nano composites, and so on. The second prospect that we have taken for 3D printed composite is technologies. We are likely to have a few sessions related to AI or machine learning based prediction modeling of 3D printed composite and how we could have simulations using an ANSYS where CAE based strategies has been used. And lastly, but not the least, we likely to see the different applications of this development of 3D printed composite. So we likely to cover a few of the sessions related to acoustic application where sound attenuation could be the target of developing those composites. And few of the industry experts we are having related to application systems in automotive. So few of them will be related to a commercial and passenger vehicle, and few sessions will be related to agricultural machinery and farming. So we have a expert session related to all these three field of 3D printed composite. So this is I likely to give a brief overview of this FDP program. So with this note, I wish you all a wonderful and enriching experience ahead, and we look forward to your participation in the impactful learning experience. With this note, I likely to invite Head of the Department, Dr. Ajit Bhosle, to please give his welcome address to the gatherings. Over to you, sir.
Thank you. Thank you, Mundi sir. Good evening all, respected faculty members, distinguished guest, Dr. Prabhakar, our principal ma'am, and dear participant. I'm grateful to extend our warm welcome to all you for the inaugural session of Faculty Development Program on 3D printed composite material technology and its application. In today's rapidly evolving world, we find ourselves coming across the several groundbreaking technologies. One of the most exciting technologies is 3D printing. Because this technology not only transfers our thinking and design directly into the manufacturing without any traditional manufacturing processes. So nowadays, 3D printing of material with the composite had application in several industries or the ranging industries from aerospace, healthcare, automotive, construction, and beyond that. Over the course of this program, we will explore the core principles and cutting edges of this technology, which will be useful for coming years in different industries. We'll get some knowledge related to the fundamentals of composite material, their structures, properties, integration with additive manufacturing technologies, then advanced printing techniques that will allow us to customize and scalable the 3D printed composites. The broad application of this composite ranging from the aerospace, automotive industries, and the medicine and the architecture, how it can be evolved with the help of this technology can be studied in this FDP. As an educator and the researcher, we will have the shared responsibility to foster the innovation and equip our next generation and the engineers with this upcoming technologies in the composite material. I encourage you all to actively engage with the session and exchange ideas and collaborate with each other. Finally, I would like to thank our expert speaker, facilitators, then the organizing team of our organizing team for a dedication to putting this program together. Once again, I welcome you all. I look forward to an inspiring and fruitful week coming ahead. Thank you. Thank you all.
Thank you very much. Welcome address by Dr. Ajit Bhosle, sir. Thank you very much, sir. Now I kindly request our respected principal, Dr. Madhuri Khambete ma'am, to please address the gathering.
Thank you, Professor Munde and Professor Bhosle. First of all, I would like to thank AICTE for giving us this opportunity to organize FDP on 3D printed composites, materials, technologies, and applications. I extend my warm welcome to today's chief guest, Dr. Pavana Prabhakar, because of her presence and the keynote speech. Definitely the stage or whatever the standard of this FDP, that will be much elevated and that will set the right tone also. On behalf of college, I welcome all the participants who have joined for this online FDP program. I also give my best wishes to the organizing team and mechanical department for upcoming this 1 week online FDP. I think among you all, I'm only the non-mechanical engineer, but still I know that how the 3D printing and the different materials, they're doing miracles or wonders in different fields. That may be the biosensors or wearable devices and automobiles. All these 3D printed devices, they are making the things happening, which probably earlier were not much thought of. Not only that is giving some of the, what I can say, that unrealizable things possible, but reducing the cost, and that is fitting in today's whatever the cost competitive environment. So this is a very much relevant topic. Very good thing that not only the materials that those will be discussed, but technologies, manufacturing, and applications, those will be also discussed in this FDP. And therefore, I think this 1 week that will give all the insights. And with this knowledge, faculty, those who are participating in this program, they will translate this knowledge to the students, and more exciting projects they will be upcoming as outcome of this FDP. With this, I once again welcome all the participants, and I extend my best wishes to the department. Thank you.
Thank you very much. This is addressed by our respected principal, ma'am, Dr. Madhuri Khambete. Now, I likely to request our today's chief guest, Dr. Pavana Prabhakar, who is the Charles D. Salmon Associate Professor in Mechanical Engineering and Civil and Environmental Engineering at University of Wisconsin-Madison. So I kindly request Professor Dr. Pavana Prabhakar, please address the gathering.
Thanks a lot, Yashwant. Hello, everyone. I'll start by apologizing. I have a cold, so my voice isn't in good shape. However, it's my great pleasure to join you all today for this exciting workshop on 3D printed composites. And I'd like to first extend my gratitude to the organizers for putting together such a great lineup of speakers on various topics in this area. As he mentioned, Yashwant mentioned in the beginning, 3D printing has revolutionized how we think about manufacturing, and it has given us a lot of flexibility for rapid prototyping. But also when combined with this exciting area of composites, that would give us tremendous opportunities to explore further lightweighting, durability, and highly customized materials to our needs. So I hope that this workshop will serve as an excellent platform for fostering collaboration, learning new areas, and as Madam Principal mentioned, take it back to the students that you teach every day. And I hope that this workshop will serve as a very fruitful experience for each one of you. And along the same lines, I'd urge you all, I'll encourage you all to ask questions, get involved in discussions, connect with peers who are participating in this workshop, and build your own network for future collaborations and possibilities. With that, thank you once again for this opportunity to address you all today. And I look forward to interacting with most of the participants during my presentation and the discussion to follow. Thank you.
Thank you. Professor Dr. Pavana Prabhakar, thank you very much for addressing the gathering on the inaugural of this AICTE-ATAL FDP. So I request Professor Dr. Avinash Shinde sir to please kindly give a vote of thanks for the inaugural function.
Thank you, Munde sir. First of all, I would like to thank AICTE-ATAL for giving us the opportunity to organize a program on 3D printed composite. I express my gratitude towards Dr. Pavana Prabhakar for accepting the invitation, and in spite of her busy schedule, he is present for inauguration and for session 1. I express a very thank to Dr. Madhuri Khambete ma'am, our principal, Cummins College of Engineering, for her constant support and encouragement in organizing such events. I express thanks to Dr. Ajit Bhosle, HOD, Mechanical Engineering Department, for guiding and supporting us throughout the organizing process. I also thank management, MKSSS, our parent organization, and our
Management Cummins College of Engineering for their continuous support and encouragement in organizing such events. So with this, I expect a great learning ahead in next 6 days, and a good learning experience everyone will expect from the renowned speakers of all the sessions. So thank you.
Okay, thank you very much, Professor Dr. Avinash Shinde, sir. So, with the vote of thanks, we're likely to end up the inaugural program of the online FDP program. So, with this kind vote of thanks, I declare the inaugural of this FDP has been done. So, now we are starting with the program. So, we are having a session 1, which is by our Professor Prabhakar. So I kindly request Professor Avinash Shinde sir, so please introduce our chief guest and the session 1 speaker to the gatherings.
Thank you, Dr. Bunde. With an immense pleasure, let me introduce our today's speaker for session 1. Dr. Pavana Prabhakar is Charles G. Salmon Associate Professor in Mechanical Engineering and Civil and Environmental Engineering at the University of Wisconsin-Madison, where she leads the Manufacturing and Mechanics Lab. She received her PhD in Aerospace Engineering from University of Michigan in 2013. Her research interests are in mechanics and advanced manufacturing of architected composite materials, with an emphasis on damage and failure of multi-physics environments. Dr. Prabhakar has received numerous awards, including NFS Career in 2021, ONR Young Scientist Investigator Program 2019, and AFSOR Young Investigator Program 2015 awards. She also received the 2019 DESTEC Young Composite Researcher Award from American Society of Composites. So I request Dr. Pavana Prabhakar, Madam, to please start your session. Thank you.
Thank you very much for the kind introduction. I'm trying to figure out, I've never used Google Meets for a meeting, so just bear with me for a second. So right now you're still seeing that screen, okay? Just give me a second. Okay, so great. So you can see the full screen, right?
Yeah, it's absolutely fine.
Okay, perfect. All right. Hi, everyone, again. Today, I'll be talking about architected flexible syntactic foam composites, primarily focusing on their mechanics and manufacturing. Here's a brief outline of my presentation. I'll start with an introduction about myself, our university, University of Wisconsin-Madison, and a little bit about our lab. And then I'll dive deeper into the topic of today, which is on architected flexible syntactic foam composites. So a little bit of background already during my introduction. I got my undergraduate degree here in India from National Institute of Technology, Karnataka. Then moved to Berkeley to get my master's and got a PhD in aerospace from Michigan, Ann Arbor. Past 8 years, I've been a faculty at University of Wisconsin-Madison. And last 2 years, I've been promoted to associate with tenure. What's fascinating is that this year, I'm actually in India because I am a US Fulbright scholar to India, and I've been hosted by IIT Madras to do research and also expand my collaborations here. And thanks to Yashwant for inviting me. This is part of my bigger picture, a bigger program of disseminating our research to a broader audience. So with that, a little bit about UW-Madison. Founded in 1848. It's a very big campus, around 1,000 acres. What's very nice about the campus is that it's very beautiful. It's adjoining one of the biggest lakes in the city. So we have 5 lakes and we are adjoining the biggest one. We have large enrollment. This is not only engineering. This includes sciences, law, business, everything. A total of around 48,000 undergrads, 34,000 graduate students. Geographically, we are located close to Chicago. We are here, about 2 hours drive from Chicago. We're doing very well in terms of our national ranking, especially the engineering program is ranked very high. So in that regard, we're doing pretty well with our engineering programs. So within UW-Madison, my lab, we study primarily composite materials for lightweight structural applications in aerospace, wind, and automotive and marine industry as well. Primarily focusing on fiber reinforced polymer composites and sandwich structures. So since it's the start of this workshop, I thought I'd just briefly talk about a very simple definition of composite materials. These are hybrid material systems which consist of 2 or more monolithic constituent materials that retain their individual properties or identities, but result in a material with improved physical and mechanical properties compared to that of the individual components. Primarily in structural composites, we have a stiff reinforcement that is bound together with a soft binding matrix. For example, the carbon fiber reinforced in a polymer matrix, which could be of epoxy, vinyl ester, or other thermoplastic resins. Looking at this Ashby plot, which shows strength versus density, we can see that the composites have strengths comparable to that of some common ceramics and metals, but their densities are orders of magnitude lower. So that is a very attractive property of composite materials. But these lightweight polymer composites, they are susceptible to damage and they can fail catastrophically under in-service loading and other multiphysics environments. Could be dynamic impact loading, a lightning strike on a wind turbine blade, long-term exposure to moisture and low temperatures, or very high internal pressure, such as in pressure vessels. We focus on 2 main aspects of composites: damage tolerance and durability. So damage tolerance is the ability of the structure to sustain damage without catastrophic failure until a time such that the component can be replaced or repaired. Or in other words, this is the load carrying capability of a structure once it has been damaged by service loads. On the other hand, durability is defined by a structure's resistance to long-term damaging effects, such as extreme temperature, UV radiation, moisture, other aggressive chemicals like salt, and stress cycles like in fatigue. Or in simple words, this is the life of a material. How long of an exposure can occur before a property dips under a certain limit. So we focus on improving these 2 aspects in composite materials through architecting, which I'll talk about. But what makes it particularly challenging to do that is the occurrence of complex failure and damage modes like delamination, intralaminar matrix cracking, fiber breakage, due to the presence of multiple base materials, multiple length scales, and how they interact with each other. But that also gives us the opportunity to tune or tailor the internal structure. We focus primarily at the micro to millimeter scales. We're not looking at nano design of these materials. So there are two interconnected research themes in our lab in this direction. We seek to establish process structure property relationships for manufacturing and designing, and study the damage and failure mechanics in multiphysics environments. Some of them that we have looked at are listed here: extreme temperatures, dynamic impact, fatigue, moisture, and also a study we've done very fascinating on the microbial impact on their degradation. Where we focus on this class of composites called architected composites, which exploit internal architecture such as hierarchical patterns and morphologies within composites, in addition to solid distribution and base material properties to achieve some unique properties that are unattainable by traditional composites. So in all of our research, we seek to answer these very fundamental questions, which are prevalent in everything we do. First, how do manufacturing processes impact in internal architecture? I'll talk about it in the context of syntactic foam composites today. Can we tailor the effective properties by combining mechanics-based designs and controlling process-induced internal architecture? A lot of this, I'll talk about in today's presentation. And how does internal architecture influence global behavior, macro-scale response under thermochemical and mechanical loading? Or in other words, multiphysics conditions. Although I will not focus on the multiphysics part in this presentation, but we will focus on how these hierarchical designs manifest globally as macro-scale response. So when I think about architecture, this is what comes to my mind: large structures, buildings, which have unique shapes and designs, but may not always, and they're also aesthetically pleasing, but may or may not always serve functionality. And when we talk about architecture in composites, they occur at very small length scales. Here, micro to millimeter length scale. So in our lab, we have three distinct areas of directions of research. In the continuous fiber reinforced laminated composites, we pioneer this area of additively manufactured patterns at the interlaminar regions to enhance fracture properties. The second is sandwich composites, where we're looking at additively manufacturing cores for and designing that from micro to macro length scale for stiffer, lightweight, and achieving snapback behavior. The third direction is looking at morphologies and patterns such as non-circular fibers within composites to achieve long-term durability under moisture diffusion and also modulating thermal transport properties. Today's talk will primarily focus on this particular topic. Before I dive into that, I just wanted to show what I meant by pattern interfaces using additive manufacturing. So the objective is to improve the interlaminar fracture toughness and strength in stiff fiber reinforced polymer composites. And the approach is to additively print patterns within traditional composites. We have a 3D printing readily available, and we can impart any pattern we like at these interlaminar regions. And the idea here is that these patterns create tortuous crack paths at the interlaminar regions, creating crack twisting and tilting, thereby effectively increasing the fracture toughness of the interlaminar regions. More about this topic can be found in these three papers if you're interested. The other topic I talked about is composites in extreme like moisture, salinity. Now, due to melting of sea ice in the Arctic region in recent years, there's a lot of interest in how the polymer composites we currently have or work with will perform in these harsh environments. So our work involved understanding how damage and failure mechanisms, primarily under impact, change under these low temperature and saline environment. This is, as you can see here, the failure mode changes from only core crushing and top face fracture to back face fracture as well. When we reduce the temperature from room to -50 Celsius. This is important to design future structures, but also design relevant repair techniques for existing composites. A more fundamental study focused on moisture diffusion, where we showed that non-circular fibers delay the diffusion of moisture through the composites and result in reduced diffusivities. Again, more about these topics can be found in these two papers. But I'd like to dive into today's topic, which is architecture snapback for composites. Here are all the previous students and current students who contributed towards this research. Everything I'm going to talk about in the next couple of minutes of this presentation is from these two papers. So all the details about the experimental and the computational work can be found in these two published papers. All right. So the objective of this research was to design and fabricate structures that can dissipate energy and achieve shape recovery without permanent set. For example, here under an impact loading excessive deformation, there's a permanent set or damage. And primarily we're focusing on sandwich composites, which has a stiff face sheet, a lightweight core, and another stiff face sheet that sandwiches the core between. Now, when such sandwich structures, for example, this could be a PVC foam core. Under impact, we see that there is core crushing underneath the impact region, and that is manifested by this horizontal plateau region in this load displacement response. So this shows that these materials currently they're excellent energy dissipators. They dissipate energy through core crushing, but they also suffer from permanent collapse or crushing. So we wanted to see if there's a way we can design certain architectures in these foam cores that can achieve shape recovery after such excessive deformation, so that we do not need to replace the entire core, but just do a patchwork or so on the face sheet. So here are our research questions. First, in the context of architected core at the millimeter length scale, can we achieve shape recovery without external stimulus after excessive deformation? We looked at concepts of negative stiffness and pseudo-bistability for that. Second, one length smaller, that is, the walls of these architected core can be manufactured with materials that introduce additional hierarchy into the foam core. So can we include hierarchy in cellular core structures to make them stiffer and lightweight? So we looked into additive manufacturing of syntactic foams for this. So first, to design our core structures, we looked at negative stiffness and pseudo-bistability. Now, elastic instability can be classified into two categories, monostable and bistable. In a monostable structure, as we start loading the structure, at some point it loses stability, it snaps through to its second stable state and continues in this stable state as we load the structure further. Now, at this stage, if we release the applied load, the structure snaps back to its original stable state. In the case of a bistable structure, shown in red, the structure, after snapping into its second stable state, if we now release the load, it settles in its second stable state. And we need to, in simpler words, in a deformed state. In order to bring it back to its original stable state, we need to apply more energy to the system. Now, there is the displacements correspondingly are shown here. Here, it's stuck in its second stable state, in the deformed state, but in the monostable, it's come back to its original stable state. Is my voice breaking?
No, it's not.
Oh, okay. All right. Other than the fact that my voice is broken, the internet is fine, right? Okay. So now there is an intermediate state between monostable and bistable, what we call a pseudo-bistable state, which is described by a time-delayed transition from the bistable to a monostable state. So this is sort of a time-delayed snapback from its second its second stable state back to its undeformed state. So this is what it would look like in terms of displacement. There is some relaxation and sudden snapback or recovery of the structure. So viscoelasticity that's inherent in materials aids this structural recovery. So can we exploit this property to allow recovery of structure to its original stable state without external stimulus? So there is a work by Brinkmeyer et al. Which showed that a snapback behavior using spherical caps made of, I believe, PDMS, a highly viscoelastic material. They showed that as they start loading the dome deforms, and at some point it snaps to its second stable state. And now, after certain or after a few seconds, upon unloading or removing the load, the structure is still in its second stable state because it's a bistable structure. However, due to viscoelastic relaxation and recovery, the structure starts to move back and then suddenly pops back up to its original undeformed state. And that's shown by this vertical displacement versus time graph, where after it goes to its second stable state, the material relaxes, recovers, and then suddenly snaps back to its undeformed state. So this motivated us to try this for our hierarchical core design as well. So what architecture to start from? That's the question. Now, there's a lot of work out there in negative stiffness architectures. I'm only showing 3 of the most relevant ones. This is by no means supposed to be a comprehensive account. So this work by Lakes at UW-Madison showed that if we have these arrays of struts arranged in this manner, it has layer by layer snap-through buckling from here to here to here, followed by a full densification once all the layers have buckled. A similar work by Bertoldi at at Harvard, I think. They showed that if we have inclined beams, you again see that and arraying them has a periodic snap-through buckling followed by densification. And all of these show this negative stiffness zones. They also showed that compared to a vertical beam, if there's an inclined beam, the vertical beam is monostable, that is, it deforms, and after removing the load, comes back to its original state, whereas the inclined beam is bistable, that is, it buckles and settles in its second stable state. Another work by Mjod in Georgia Tech, this was the most relevant for us, where they had these sinusoidal inclined beams, and again they showed this periodic snap-through buckling. They also showed that heating it up, they were able to get the structure back to its original stable state. Now, with this in mind, we wanted to extend this design to a 3D structure, especially for foam cores. So we started with a baseline sinusoidal shape, and using convolution in 2D, we extended this to a 3D structure, which is very similar to an egg crate that you might have seen. And the unit cell is as shown here. This is quite complex to start with and parameterize it. So we looked at two extreme designs, a truncated cone and a dome structure. And some initial study, and as expected for the same wall thickness, showed that the cone has a higher initial slope in its low displacement response compared to dome. And because we want adequate stiffness in our core structures, because we are looking at these as potential for sandwich structures, we chose the truncated cone as our choice of unit cell. We manufactured this using stereolithography. It's a 3D printing technique where we start with a resin shine light layer by layer as shown here to create a 3D structure. We used thermoplastic elastomer because we wanted sufficient viscoelasticity in the material. So we created these truncated cone structures, arranged them as shown here. This is just one layer of these truncated cones sandwiched between stiff facings. We can create multiple layers by 3D printing them accordingly. So first, we wanted to measure the snapback response. Typically, when we load these structures, we have a loading platen, let's say in compression. Let me play this video. As you can see here, we have a flat platen that's compressing these, the buckling. And as soon as you unload it, the loading platen immediately comes back to its original state. It is not recording how much the structure itself is snapping back or deforming back to its original state, which is shown in this displacement time graph in red here. So we load, we immediately unload it, and this is the measurement. But we want to see how much the top face of this individual unit cell moves with time to measure if there is any time delayed snapback, sort of the behavior shown here. So there is relaxation and then sudden snapback. So for that, we designed this fixture, which is expanded here. Basically, it's made of a flat platen here with a hole and an LVDT attached. So the loading from the test frame is acting on this flat platen, which is compressing the core or it's compressing the unit cell. And the LVDT is always in contact with the top face of that unit cell. And upon unloading, as you can see again here, so the LVDT is in contact with the surface. It is still in contact with the top face of the unit cell, thereby recording the entire displacement time response. So we use this to validate some of our simulation of this snapback behavior. Talking about simulation, we developed computational models to capture the snapback response, thinking of a sandwich core in mind, which can be subjected to a 3-point bend structure. We see that the unit cells can be subjected to both compression and lateral force in these regions. So we applied both compressive and lateral force individually on these to capture the effect of compression as well as shear on the unit cells. We non-dimensionalize these geometric parameters into 3, alpha, beta, and gamma. Alpha represents the thickness of the unit cell walls, T by L. Beta represents the slope that the walls make, H by RP minus RS. And gamma represents the curvature of these unit cells. So we modeled and simulated this in Abacus. And the inputs to this were the viscoelastic response of these material. So we used hyperelastic Monet-Rivlin model with viscoelastic properties as Prony series, as shown here. And the input to these were obtained by performing relaxation, that is tension, hold the specimen and allow it to relax. And we fitted that with the Prony series. And here's a response to show that these parameters for the Prony series do a good job at capturing that viscoelastic relaxation. And using these parameters, here's an example of how the structure deforms when loading it, and then the materials has some relaxation, which is followed by, maybe I should, I'm not able to forward it, but as you can see, at that stage, it immediately snaps back. So this is the response that we are expecting when we have a good combination of geometric parameters and the viscoelastic properties. So with these simulations, we developed process maps or design maps, where basically we have alpha, which is the thickness in the x-axis, the slope in the y-axis, and each of the columns is corresponding to different curvatures, that is decreasing curvature from left to right. And the first row is for just pure compression case, and the second row is a combination of compression and lateral loading. So we have three examples here. I've just chosen 3 random cases. As you can see, the top one immediately comes back to its original state upon releasing the load. The third one is still stuck in its second stable state. It's not come back. Whereas if you notice, the second one has a time-delayed snapback. So this is pseudo-bistable, monostable, and bistable. And here in this graph, you can see that as alpha reduces, that is, we have shallower structures, thinner structures, and as beta reduces, shallow structures, we have monostable. Also, if we increase the thickness, we have a large range of monostable structures. Now, in red is the bistable behavior, which basically corresponds to very steep slopes and very thin walls. So that is this region. And if you see here, this third case is that we have a very thin with a very steep slope. So for these Prony series and for this viscoelastic material, we get a band of geometric parameters where we can achieve this pseudo-bistable behavior. And as expected, as we increase the lateral loading, that is eccentricity, that zone reduces, because now the lateral force is pulling the structure back to its original undeformed state quicker. So given your material, you can develop these maps and choose the parameters for your geometry to suit your needs, whether you want a bistable structure, pseudo-bistable, or a completely monostable structure. So here we picked 2 points, and here are some examples of how we can arrange these cones. Now, this work is not meant to give you this best optimal design configurations, but these are some ideas of how these can be configured for different applications. So here we have a cuboid with these truncated cones on all faces, and this is a printed structure. And we're doing compression. As you can see, we have layer by layer buckling of those cones, and then the snapback response. Here's what we call a club sandwich. So we have stiff face sheets or stiff composites that are distributed with truncated cone structures, printed ones between. Here's a 3D printed structure with face sheets, 3 face sheets or 3 stiff composites. Here are some more simulations of how they would behave under a point load. We can also use this for reconfigurable structures. As you can see here, they can be compressed into a compact structure and released where needed. So this comes to the end of my first part of this talk. That is, we proposed an alternate sandwich core design using viscoelastic architected structures. The viscoelastic relation of the material introduces an intermediate state of stability between monostable and bistable in the form of a time-delayed recovery, or otherwise known as pseudo-bistability. And due to this pseudo-bistability, structures are designed to buckle and collapse to dissipate energy and recover on their own after a certain period of time, exhibiting structural resilience. Design maps that were constructed by computational modeling showed that a small range of geometrical parameters result in bistable or pseudo-bistable, and imperfection reduces it further. Some future work are to explore other design possibilities for sandwich cores, and also how to make these stiffer and lightweight. As you saw, these structures were quite flexible, so not ideal as a core for a sandwich structure. So how can we make them stiffer while keeping them lightweight? That creates a nice segue for the second part of my presentation, which is on additive manufacturing of syntactic foam composites. I can pause for a second if you have any questions, or we can keep it for the end as well, however you'd like. Should I continue?
Yeah, please. Yes.
Okay, sure. Now, the objective here is to enable additive manufacturing or 3D printing of architected syntactic foams for these sandwich cores. Here's the idea. We touched upon this part, which is architecting at the millimeter length scales. Now we want to introduce additional level of hierarchy by creating segregated matrix regions in these walls of the unit cells with embedded particles within them. The material, which is in this case a thermoplastic polyurethane, TPU, inherently is a composite at the nanoscale, where they have hard domains which are arranged hard structures as shown here, which are hydrogen bonded, and they're surrounded by more flexible chains of polyols as shown here. Now in our work, as I said earlier, we are not manipulating these aspects. We are fixing the hard domains in our structure, in our material, but more so tailoring the internal architecture at the micron length scale. So what are polymeric syntactic foams? These are closed cell composite foams with thin wall hollow microparticles or microspheres called microballoons, which are dispersed in a polymer matrix resin. These are used widely in marine applications for buoys, as well as underwater remote operated vehicles like Alvin, as shown here. So because of this closed cell structure, they provide excellent mechanical properties like high strength and low density, in addition to lower moisture absorptions compared to open cell foams. So in this work, we are printing these cell walls with polymeric syntactic foams. So we chose selective laser sintering to manufacture these hierarchical syntactic forms. I'll tell you in a bit why. So we're looking at the effect of parameters. That is, how does changing the print parameters affect the quality of the printed material? Second, how does changing the volume fraction and the size of microballoons influence the morphology and the mechanical performance of the foam? And last, how do printing these hierarchical forms with architectures? What are some differences between the architected forms printed with pure elastomer and compared to those with the microbubbles embedded in the cell walls? So next few minutes, I will try to answer these three questions for additive manufacturing of syntactic forms. So the constituent materials, as I said, TPU, with these properties as shown here, and that's because they have some level of inherent viscoelasticity. And then we embed glass microballoons, GMBs is what I'll call hereafter. We chose 3 grades of GMBs with different sizes and the crushing pressure as shown here. The particle size reduces essentially. We go from 60 micrometer of mean particle size to 22 to 15. The syntactic form that we print, we use this nomenclature. SF stands for syntactic form. The first number here is the particle size, that is 60, 22, and 15. Dash VF will be how much volume fraction of these individual particles are we adding to the TPU powder. As you can see here, we chose particles. TPU is in the powder form, and these microballoons are also powder-like structures. So when we combine or just mix them, TPU and GM60, the GM60 particles are comparable in size with TPU, whereas the 22 and 15 are very small compared to the TPU powder size. So keep this in mind because we'll talk about that later on, the effect of particle size on the foam properties, morphology and property. Right. So we used sintered laser, the SLS printer, and we incorporated material GMBs in ratio 20, 40, and 60 by volume. And we looked at 2 print parameters primarily, laser power ratio and layer height. So in an SLS, we start by this powder mixture in the feed bed, which is rolled onto the print bed, and a laser is shined onto this powder mix, which locally sinters the particles together, and then the print bed is moved down, and the next layer of material is raked onto the bed, shining laser again, creating the next layer, and so forth, building the full 3D structure. So, the power of this laser is one property or parameter we modify, and also the layer height, how much refinement in layer height can we achieve with this process. Okay, so we started with just pure TPU first and try to understand the effect of these print parameters. So here we looked at something called LPR, which is the laser power ratio. 1 implies a laser power of 3 watts, and then 1.5 and 2 is just times that value. This is the limit of the power SLS printer we used, but it was to our advantage because it gave us some unique internal architectures, such as these segregated regions when we used this low laser power ratios. Our layer heights, the default is 0.12 millimeter, and we could go to 0.05 millimeter and 0.15 millimeter as the 2 layer heights. So first we looked at the tensile performance. As we increased the laser power, we saw that the strength of the modulus increased. And with increase in laser power and decrease in layer height as well, we saw that the tensile properties increased. For example, in star here is laser power ratio of 1.5, but with reduced layer height. So we see that there is a slight increase in properties when we reduce the layer height as well. So we chose 1.5 and 0.075 as our parameters to print the consequent structures. We could go to 2, but we would be reaching the limit of the machine, so we did not want to mess with that. So we, and 1.5 did show an increased wall thickness. Here, when I say walls, these are the walls of the segregated TPU material, not the cell walls of the unit cell that I've been talking about in the previous part. So cell walls here is the wall, these regions basically between the porous porosity. We saw this improvement because with increasing laser power ratio, we effectively changed the supplied energy to the powder, and we saw that manifested in increasing this ratio between the peaks of the C double bond O band to the right and to the left at this in this section. Basically, this signifies the ratio of the hard domains, which are basically the organized regions that are formed within the TPU versus the soft domains. So because we are effectively increasing the formation of hard domains in the TPU by increasing the laser power ratio, we saw this improvement in the mechanical performance. So then we added fillers. So we wanted to see how that changes the internal architecture and structure of these foam composites. So here are images. I'm showing only for the 20% fraction as an example. And this is for the bigger GMBs with mean dia of 60, 22 smaller, and 15 the smallest particle size. We see that the bigger GMBs tend to get lodged between and within the TPU, sort of creating a bridge between these segregated TPU matrix regions, while the smaller particles were completely embedded within the cell walls, as you can see in these two cases, especially in this one. That also resulted in a reduction in the cell walls, as is apparent in this in these SEM images. So we showed this for the first time that GMB particles dictate the cell wall size, and this is attributed to higher scatter of the supplied laser energy due to higher particle density per area in the powder blends, with the highest in the smallest GMB particle case. So we wanted to see how these manifest as mechanical properties. First, in tension. As expected, as we increase the volume fraction for a fixed particle size, the strength dropped and the moduli stayed in the same region as shown here. The strength is attributed to poor interfacial bonding. We did not do any surface treatment before we printed these. These were as received particles. So it's expected that in tension, it would perform not so great. Now, effect of different GMBs, we saw that as the GMB particle reduced from bigger to smaller, the strength drops, and so does the strain to failure. That is, the foam tend to become more brittle as we go to smaller particles. But our main focus was in compression because of these high pressure conditions in underwater vehicles and things like that. So we wanted to understand what is the performance under compression. So here we see that as we increase the volume fraction. So we fix the, we change one parameter at a time. We fix the particle size to the largest particle, 60, and we change the volume fraction from 20, 40 to 60. We see that increasing the GMB content, the strength dropped. And this can be attributed to lower crushing strength of the GMB particles. As you may recall, the larger particles have the lowest crushing strength, and they also create bridge between the cell walls, causing their compression and collapse, resulting in this reduction of the plateau region. Now, an increase in moduli was observed as we increase the volume fraction, but up to a certain extent. Here, please just focus on the squares, markers, because we're only changing the volume fraction for a fixed particle size. So up to 40% volume fraction, we see an improvement, but beyond that, we see a dip because there isn't sufficient matrix to bind this higher percentage of volume fraction of particles. And we see that as we reduce the particle size, this peak value, the volume fraction corresponding to peak value shifts to the left. That is, smaller particles creates further disintegration of the syntactic foam. So focusing more on different GMB sizes. So we fixed the volume fraction at 20% because we saw the very good properties at that small volume fraction. So we see that as we reduce the particle size, the response gets closer to the original TPU. As you can see here, the gap is closing. This is because, especially the strength, the particles are all embedded within the cell walls. So first, the walls of the segregated region have to come in contact, and only then the particles embedded in the walls will start to get stressed and try to collapse, which maybe they won't even collapse because of extremely high collapse strength of the smaller particles compared to early crushing of the larger particles. I'll talk more about this next, which is, so we performed 2 cycles of compression loading to understand whether the particles have crushed or not. As we can see here in this first figure, this is corresponding to a pure TPU. We load the structure first to 30% and then unload it. And then the next cycle, we load it to 50% of 50% strain, global strain. So here we see that with the larger particles, it's a bit crowded here, but basically if you look at the solid versus the dash for each category, let's say for the black, which is basically 20% volume fraction, we see that as we load it to 20% and unload and load it again, it follows the same response. That means the particles have not crushed as much. However, if we load it to 30% in red and then unload it, we see that there's a significant reduction in the initial slope here, which means that the particles have crushed and the stiffness has dropped in subsequent cycles, which we do not see for cycles 1 and 2 in this red and black in these 2 cases. Whereas in blue, we do see some reduction because in that case, we have compressed the foam up to 50% strain. So we do see some difference in the solid blue versus the dash blue line. So in a nutshell, when we strain the foam to 20% strain and then reload it up to 50%, we see that the pure TPU and the ones with smaller GMBs have no difference practically, whereas the ones with the bigger ones do show, and this difference increases tremendously when we load the first cycle is to 30% strain and the first cycle is at 50% strain, indicating severe particle crushing in these and very little or none in these two. So this also indicates that we have very good densification when we have smaller particles of GMB reinforced in these TPU foams. So the last one is how now this difference in stiffness and densification manifests in the architected cores. So here we see that, before that, we consider two types of architected foams. One is bending dominated and the other is stretching dominated. So in the bending dominated, which are gyroid, diamond, and honeycomb, the main mechanism is the walls of these architectures come in contact, compress, and cause collapse of particles. Whereas in the stretching dominated one, which is the tilted honeycomb key, and conical that I talked about in the first half of my presentation, the key mode of collapse or compression is through buckling of the cell walls, as you can see in these two cases. Okay, so here we see that the stiffness, that is the initial slope of the load displacement response for all these increase as expected when we added GMBs. Here we have particularly considered the larger GMBs because of higher stiffness expectation. As I mentioned earlier, that the bigger GMBs, because they cause they create a bridge between the segregated matrix, increase the stiffness, whereas the smaller GMBs, because of their higher crushing strength and which are embedded within the segregated matrix, creates higher densification stresses. With higher stiffnesses in mind, we use the larger particles to reinforce here. So we see that because now the walls of these architectures, the stiffness has increased. It manifests as increase in stiffness, and weight normalized increase is even higher. When we compare densification stresses, the bending dominated ones showed a reduction or a drop in the densification stress, whereas the stretching dominated one showed an improvement. And this is primarily because of the change in mode of crushing. So in this one, this is just particle crushing mechanism. And because the larger particles crush easily, we saw a reduction. Whereas here, because it's the peak or the densification is related to the buckling of the cell walls, it depends on the stiffness of the cell walls rather than the crushing of the particles. And that's why we saw an improvement in the response here. So this was very informative. And this can sort of aid future designs to be more stretching dominated to achieve higher stiffness. Here's a process structure property relationship map developed where we show that as we increase the energy density, that is the energy supplied during the printing process, we go from a segregated matrix to a solid matrix at some point as expected. But as long as we're in the segregated zone, the larger particles have higher compressive modulus compared to the smaller particles. Also, there is a limiting volume fraction beyond which the compressive modulus decreases for both bigger and smaller particles, and that volume fraction limit moves to the left or it's reduced when we have smaller particles. In terms of compressive strength, we see that as the energy density increases, the compressive strength increases because of better contact and confinement of the particles, and the smaller particles show a higher or a higher improvement in the compressive strength, and in both cases the strength decreases with increase in volume fraction. So we want to limit that to a smaller volume fraction. Now, with all this said, how do these forms perform in the grand scheme of things? Here's an Ashby plot of compressive modulus to density. We did not compare strength because everyone has different ways of picking the compressive strength. Some may have a plateau strength, some may say the densification stress of the compressive strength. So we did not do that. Instead, we focused mainly on the modulus part. And here we see that here are some polyurethane rigid forms, PVC cross-linked forms, and here's our forms at this stage. These are some epoxy-based, very stiff forms, so we will not compare them here. However, right now we have the strength slightly lower, but in a reasonable density range. But with architecting and increasing basically the inherent hard to soft segment ratio, which we did not change in this case, we can push this up in terms of the modulus, and then architecting them, which would create some hollow regions, would reduce this density, but also reduce the compressive modulus a little bit. So this is what we are striving for going forward, manipulating the hard to soft segment ratio in the viscoelastic material we are looking at and further architecting. So in summary, we shed light on the mechanics of additively manufactured syntactic forms with segregated matrix. We showed how AM parameters can be coupled with GMB parameters to achieve desired mechanical response or tune them, the mechanical response with such segregated matrix. We demonstrated for the first time that when we have such segregated regions, the microballoon size dictates the cell wall thickness, and also decides whether we have a stiffer or a high densification stress in these syntactic forms. The influence of microarchitecture on the macro-architected syntactic form, that is how embedding these micro scale particles manifest differently when we choose stretching dominated versus bending dominated architectures under compression. Some ongoing and future work, we are looking at the impact response of these architected polymer composites. We've done a fair bit of work in the thermal, dielectric, and viscoelastic response, a measurement of these syntactic forms. There's a published paper here and an archive paper here if you're interested further to read about this, primarily in view of marine and oil and gas industries, where we can use these perhaps for underwater cables and pipelines due to their excellent insulation properties. Some potential application of these flexible syntactic forms, when we're looking at morphing wings or blades, these provide a very good lightweight alternative to tune how the blades and wings can be made flexible, extending the chord or changing the shape of these wings and blades in either an active or a passive way, because they require very little or no energy to switch between different modes during shape change. So with that, I'd like to conclude saying Can we print stiffer and lightweight architected syntactic foams using SLS? Yes. Can we choose print and GMB parameters for a specific application? Yes. And can we couple print and GMB parameters to tune the mechanical response of syntactic foams? So we have, yes. And so we have answered all three questions in this work. So with that, thank you all for listening. And I'd like to acknowledge funding from several agencies over the years who have funded our lab in general and ONR Young Investigator Program to fund this specific research. So with that, thank you, and I'm happy to take questions at this point.
Yeah. Thank you, Professor Pavana. Dear participant, I kindly request to please raise your hand, and then I will take your name to ask the questions. Or if you want to type your questions, you can put your questions in the chat box. The forum is open for Q&A and the discussion. Dear participants.
Good evening.
I can't hear you.
Your voice is not clear, Anish.
Hello.
Yeah. Please.
Actually, this session is very nice session and very informative session. Myself, Anish Dev from Asansol Engineering College, West Bengal. Can I have Madam's contact details? So in future, if we want to connect with her or any research or collaboration purpose, can we get her details?
Yeah, surely the details is available. If you search with her name, and the email ID is available on her website and her web page also, you can connect with her as and when required. So I will move ahead with the technical questions from the audience first. So there is a raise hand from Professor Venkateswaran.
There is a question in the chat box. I can answer that.
Yeah.
So how do we ensure uniformity in dispersion? So we use a mechanical mixer with certain time and RPM fixed for each case. And after it's thoroughly mixed, we put it under an SCM to see how well the dispersion occurs. We did not measure the dispersion as such, but when we looked at the printed material, we see that there's a uniform or quasi-uniformly dispersed particles within the foam. But because these are all in a powder form, they can be easily mixed mechanically.
Yeah, there is one more question from raise hand from Dr. Ganesh Purikar. Professor, please proceed. Please ask your question. Dr. Ganesh Purikar, unmute your mic.
Can you hear me?
Yes, we could.
Yeah, Pavana ma'am, it was a good session. My question is related with what different matrix material as well as the reinforced materials that can be considered considering the specific applications of this.
Yeah, absolutely. So that's a great question because GMBs, we chose them, glass particles, because they're more controlled and we have cell walls which are pretty well made in an industry setting. However, we can use other hollow reinforcements like cenospheres, which are waste particles. They can be introduced as well and studied in a similar manner. And because the most of the viscoelasticity comes from the matrix, we can essentially choose any particle as reinforcement to get this kind of response, as long as we have sufficient viscoelasticity in the matrix that we're choosing. So we chose for the matrix TPU because we know it has a good level of viscoelastic relaxation, but we can use silicone, PDMS. These are more on the much softer side, but also a few thermoplastics can be used which show such viscoelastic relaxation behavior. So anytime you want to start looking at newer materials, the first thing is to measure their relaxation, study how much percentage of relaxation is achieved with time, and then, as I showed some of the maps, develop such maps to study, okay, is this material suitable for achieving snapback behavior? But if you're not interested in snapback and just interested in higher strength and stiffness, you can choose basically any material which can be 3D printed to and in the powder form, because that's what we're using. We didn't have a lot of success printing these in the resin form because the particles are so light that they were all accumulating top. Basically, they were rising, and that uniformity was not maintained.
Okay. One more point. How the uniform mixing of the powder that is being confirmed in this case?
So we did a post study after printing them to see whether the particles are through the thickness uniformly distributed. But essentially, because of the powder nature, and we're using a mechanical mixer to do that, we are at the outset assuming that it's uniform, and then we are verifying it after in the cross section.
Yeah. Thank you, ma'am. Thank you.
Thank you. Thanks for your questions.
Next raise hand, Amruta Ranaure. Could you please ask your question?
Yes, good evening, ma'am. Ma'am, I had question related to the SLS printer which you have used. Was it customized according to the requirement of research? And how much did it cost for that
Sure.
printer?
So no, this was not customized. This was a kit that we bought from Prusa, I believe, which came assembled. We opted for the assembled version. It was around $10,000 because the laser power is quite low. We didn't have like 30 watts and such, which we did not want for this work. But if you want a completely solid part, then you would need to go to higher powers.
And ma'am, was the laser modified? Means, as you said, that.
No, it came with a 3-watt laser, so we just used that.
Okay. Thank you, ma'am.
Thank you, Amruta. There is a question in the chat box. What are the research facilities required for maintaining uniform particle size?
It's a V-shape hopper mixer that we got, and that was used to mix. But to characterize, we used SCM to basically visually confirm that it was uniform. You could also potentially do microscopy by polishing and looking at the surface of at different cuts. You could also do micro CT scans at very high resolution to measure the same. CT scan would be non-destructive, so you could use micro CT scanning as well.
Okay, yeah, thank you, ma'am. Another question is, can any other thermoplastic be used for the foams other than TPU?
Like I said, you can use, we have worked with collaborators at IIT Mandi, with whom we have looked at HDPE printing. I'm trying to think. Yeah, HDPE is the one that we've used extensively to 3D print with hollow particles embedded in them. Now, the viscoelasticity has to be measured and studied for snapback. But if you're only interested in an architected foam core with microparticles embedded, then HDPE could be a potential thermoplastic.
There is one more question from Mr. Praveen Dandore. How to select the combination of material for making composite material? Is there any thumb rule for the same?
Again, it has to be an application-driven selection. What is the application you're looking at? What is the best choice of materials for that? So it's very dependent on what your end goal is. For example, whether you want high stiffness, you want high strength, you have high fracture properties, you want higher energy absorption. So these are all, from a structural engineering point of view, important aspects to think of while selecting your materials. So yeah, really there is no thumb of rule as such, but it's very dependent on the properties that you're looking to enhance.
Yeah. So there is one question from Himanshu. I think he's a PG scholar asking for kindly suggest a PhD research topic in this particular area.
Oh, yeah, yeah, that's a very difficult question and an open-ended one. So, like I said, high compaction, because we're looking at these for undersea applications, for example. How do they perform in the extreme pressure? That's something of interest. If you're looking at, again, more on the marine side, moisture is a big issue. So how do we improve moisture resistance of syntactic foams? Yeah, I mean, there are endless topics that we can think of to do research in this direction. So yeah, I unfortunately I don't have like a like the $1 million research idea to say, but yeah, that's something you need to look at the literature and say where's the gap and go from there.
Yeah. One more question, that can we print some composites for acoustic applications like noise absorption by kind of this architected composites?
Yes, of course. I mean, there is a lot of work being done. I think one of the presentations in this workshop will be in that area of acoustic absorption. So, yeah, you'll have to, but certainly we can print for acoustic absorption as well, similar to energy absorption for damage and such. Yeah, for sure.
One more question. What could be the suitable proportion of matrix and enforcement to get the uniform mix?
To get a uniform mix?
Means uniform is. Dr. Nitin Pagar, could you please elaborate what exactly you likely to mean? Uniform mixture you are meaning likely to see, or meats? We could not able to understand. Mixture. Yeah. Proportion for uniform mixture.
We didn't really focus a lot on a limit for that. But we do see that if we go to 60% volume fraction, they weren't really binding. So I think that is, there is uniformity in general, but there's not like a percentage for uniform mixture here. Perhaps that's a study one can do to see the sensitivity of mixing on uniformity.
Okay, so I think there is no more question in the chat box or there is no raise hand. So all of you have got the answers to their questions. Is there anyone have a question? Last 1 minute. Okay, to the just additional information to the one of those participant question that related to any other thermoplastic. Dear participant, we have a session on Friday, 10th of January, of Dr. Mrityunjay Dodmani, who likely to give a more detailed information related to the other thermoplastics 3D printing. So that session will be very helpful. And I think Pavana Prabhakar was mentioning about Professor Dodmani only.
That's right. That's right. Yes. We have worked a lot in collaboration over the past decade or so.
Yeah. Okay, so there is one last raise hand. So Mr. Sachin Pawar, please ask your question.
Hello.
Yeah, please.
Am I audible?
Yeah,
Yes.
you're audible.
Hello, ma'am. I work with Dr. Kara Peters in North Carolina State University on the aerospace composites for impact properties.
Mm-hmm.
And I want to extend that research for the 3D composites for the impact properties.
Mm-hmm.
Are you working on these same things?
You mean 3D printed foam or 3D printed composite?
3D printed composites like CFRP.
CFRP. We are looking at some 3D printed thermosets work,
Okay.
but that's not been the main focus of our research lately. So our 3D printing is to improve existing structures as interlaminar reinforcements and things like that, not necessarily printing the continuous fiber structures.
Okay. Thanks a lot.
No worries.
Okay, so with this kind note and permission from the speaker, I likely to give a vote of thanks for the first session of day one. So I very much thankful to Dr. Pavana Prabhakar for giving us first inaugural talk as well as the session one to the audience of this ATAL FDP on 3D printed composites. So I hope everyone has gotten very good insights in the topic of 3D printed composites in the context of architected composites. So I'm very much thankful to our first session speaker, Dr. Pavana Prabhakar, for sparing his valuable time. Even his throat was not so good. Thank you very much, Professor Pavana. Also, I'm very much thankful to our sponsor, AICTE-ATAL, for sponsoring this FDP and giving an opportunity to us to organize such events. So I'm very much thankful to the AICTE-ATAL. So with this kind note, I'm very much thankful to Dr. Pavana. I'd like to say thank you very much.
Thanks for the opportunity. I really enjoyed interacting with everyone and answering the questions to my best ability.
Yes, thank you, Professor.
Bye.
Dear participant, please be on the same line. We'll have a second session in couple of minutes. The second session speaker are joining in couple of minutes, so please be on the same line. Okay, so hello, yeah. Good evening, one and all, again to the day one session two. For day one session two, we have a speaker with us, Dr. Gurminder Singh. Dr. Gurminder Singh, could you hear us?
Yeah, I can hear us.
Okay, yes.
Yeah. So hello everyone, good evening.
Yeah, good evening. So before start of this day 1, session 2. We have just finished up with the session 1 of Professor Dr. Pavana Prabhakar. And before start with the second session, I would like to introduce the speaker of the session 2. So, dear friends, dear participants, we have with us Dr. Gurminder Singh, who is currently working as an assistant professor at Department of Mechanical Engineering, IIT Bombay. He worked as a postdoc researcher in School of Mechanical and Materials Engineering at University College Dublin, Ireland. And prior to join the University of College Dublin, Dr. Singh was a postdoc fellow at University of Grenoble-Alpes, France, where he has research was focused on experimental and simulation studies of extrusion 3D printing of metals. Dr. Singh was a Gandhian Young Technological Innovation Award for the development of 3D printing method for the fabrication of patient-specific stains in 2020. Dr. Singh obtained his PhD from IIT Delhi. His PhD work was focused on development of low-cost, rapid manufacturing technique using ultra-vision vibration-assisted sintering and 3D printing. His PhD work was featured by 3D Print website in February 2020 edition. He has published over 50 articles in peer-reviewed international journal, conference proceeding, and book chapters. He has published in leading journals such as Additive Manufacturing, Material Science and Engineering, the Journal of Manufacturing Processes, Rapid Prototyping, etc. So with this kind introduction about session 2 speaker, Dr. Gurminder Singh, I warmly welcome to you for the second session, and I kindly request to please proceed with your session.
Thanks, Yashwant, for the introduction. So I can share my screen.
Yes, please.
I hope you can see my screen.
Yes, absolutely fine.
Okay. Thanks for this opportunity to interact this FDP. So I think it's a late evening, let's say dinner time for everyone. So, but we will try to have a better interaction so that you can have a good mood at the end of the day. So please feel free to ask any question in the middle of the PPT even. Okay, you can raise hand and you can just unmute yourself and can give just any question. So today I will present some unconventional method, which is a low-cost method, so which can be used in 3D printing to fabricate very difficult materials. Okay, so like I will give you example of copper. Copper is very difficult to print by lasers because having high thermal conductivity, and when the laser is falling on copper material, so copper material is reflecting that laser and not able to sinter proper, okay, to get 100% density. Okay, so I will give one method which is alternative method and can go up to 100% density. And other example like material are some ceramics which are having a very high melting point, which is more than 3000 degrees Celsius and more than even 4000 degrees Celsius. It can easily fabricate by this method, and some very crack propagated materials, which is during solidification getting the huge stress shielding effect and getting cracks like some nickel based alloys, like even Inconel 718 is very difficult to make by laser, but it can be easily fabricated by this method. Okay. So additive manufacturing, for me, additive manufacturing is a layer by layer method. Okay, wherever you are using a layer by layer technique, so it is additive manufacturing method. But in additive manufacturing, like there are a number of definitions. Like people are saying using it for fabricating direct parts, and people are using it for to make prototypes. Okay, so when you are using it for prototype, okay, when it is using is not as a end product, but it is as a first prototype where you are redesigning it and using it as a basic benchmark to make tooling. Like for injection molding, you can design first your dies. Okay, you can see how the dies are performing, and later on by machining you can make the last die. Okay, instead of doing remanufacturing again and again to get a last product of the die. So that comes under prototyping. And when you're using this 3D printing product, additive manufacturing product as a final product, that is comes under rapid manufacturing. Okay, like there are some implant images given. Okay, this is implant for skull, so that can be used as a direct product. So you don't need to use any other process to make it. Okay, so you can use hip implants. Okay, so now these days the engine nozzles are made by 3D printing. That is as a final product, which is comes under rapid manufacturing. So rapid manufacturing, these are the basic steps. So I'm not going in detail, like making a CAD model, then making a changing it to tessellation. Okay, I hope everyone knows what is tessellation. When we are changing, approximating the surface of a 3D CAD model into triangles. Okay, so there is always some gap left. Like this is a triangle, and you're having your CAD model. This one, there will be always a gap. Okay, so that is a problem in 3D printing. Okay, which can be rectified by having very high resolution of tessellation, but it makes your product, your size of the file very large. Okay, but still at the end of the day, you will not get a smooth surface as you required as a CAD model. Like this is a sphere. Okay, you can't get a definite sphere. You have to do a lot of post processing to remove the edges, very small edges of the triangles when you have printed it. Okay, so there are other methods like you can avoid this tessellation. Okay, so that is not our topic of the day. Okay, so after tessellation, there's a slicing steps. Like you have to slice this triangles in a particular plane to get the points in which you will have to make a loop in which your laser or in which your 3D printed in FDM, your nozzle is moving, it extruding, and it is filling the gap to make a XY cross section. Okay, so then after getting this G code, you have to use any 3D printing system. It can be FDM, it can be SLM, it can be SLS, it can be DED, it can be a DLMS process, it can be any type of process, and which is using this G code to make a similar part which is made by CAD model, and then later on we are doing some post processing. So this method comes under direct rapid manufacturing. Okay, you can directly make a part and you can get a last geometry. Okay, but now as I given the example, like you have to make a copper. Okay, so copper is very difficult to make by this process. Okay, copper, like example is you can have to make aluminium, which is very difficult to fabricate. You have to fabricate silver. It is not possible to make silver products by using this RP, any traditional RP system method. So you have to go through different indirect methods. Okay, so I can give you a couple of examples of indirect methods. Like already we are using indirect method in as a investment casting. Okay, what we are doing when we are using for the casting, we need a pattern. So that pattern we are fabricated by a polymer 3D printer. Okay, so you are having a polymer 3D printed part. So it can be FDM, okay, it can be SLS, it can be SLA, it can be any type of process. Later on, you are using it to make a mold. Okay, you are having a mold. Okay, you are filling it by investment material, and then you are moving it. Then you are getting some space, and you are pouring some melted liquid to get a final shape. So that is a traditional process of investment casting. So this also comes under an indirect rapid manufacturing. Okay. So you have made the last part, but it is not a directly 3D printed. It is indirectly. You are using 3D printing as a component. Okay, and you are using any other process like a casting, which is making the final product of metal. Okay, so you can use aluminum casting, you can use steel casting, any type of material which is available for casting can be used in this process. But there are many limitations. Okay, like when you're casting, you don't have good mechanical properties. You have to do thermal treatments. Okay, so that is also problems in this process, but it is handy to make any shape. So now we can use this polymer 3D printed by combination of another process. Like having a polymer 3D printing, I can do metal spray on it. It will be conductive in nature. Okay. Like we know EDM process. Okay. In EDM, we need electrode, which is basically of conductive in nature. Okay, only role of the electrode is to pass the current. Okay, like we are using copper-based electrodes. So instead of making a whole solid metal part, so you can use a polymer 3D printed part and can do spraying on it, copper spraying. Okay, you can do copper paint also, which is conductive in nature. Okay, then you can pass the current. It will pass through the conductive channels, and you can do EDM. But there will be EDM will be not perfect, but for the complex shapes, it is very handy for very small wear rate. Okay, so it can be clubbed with the cold spray process. Okay, where you are having a wire and you are heating up at high temperature, and by the kinetic energy you are trying to join these small powders, and you can join these small powders with polymer 3D printed part. Then you can get a metal part. So another process is electroforming. Like another process is investment casting, which I shared. Okay. And another process is sintering. Okay. So instead of using casting, if you use sintering, so sintering is always having an advantage as compared to casting. Okay, like it does not have residual stresses. It has good melting, good mechanical properties as compared to casting components. So in sintering, you don't need melted liquid. You just have to go up to 60 to 80% of the melting point. Okay, you don't have to go large. Like you have to sinter 3000 metal, which ceramic, which is having 3000 degrees Celsius temperature. You can easily sinter it as 1800 degrees Celsius or 60 around 1900 degrees Celsius. You can easily sinter it. So that is the advantage of sintering. So we will see how we can use polymer 3D printed part combined with sintering to make metal parts. Okay. Now you don't have laser. There is no laser. Okay. There is no electron beam source. So joining of the metals is by conventional induction heating. Okay. Whatever the source of heating in the furnace. It can be microwave furnace also. Okay. But you don't have laser. Okay. Which is a mean reflecting when you are falling it on the high thermal conductive material like copper. Okay. So by combining the polymer 3D printed part and the sintering, we can easily make copper 3D printed parts. Let me show you some. So to understand the sintering, so we need to understand some mechanism first. Okay. So mechanism is how the sintering works. Okay. So sintering generally works when you're having metal particles which are very nearby. Okay. And metal particles are nearby and joined at the not joined, but they are packed at the boundaries. When you are heating up to near their 60% to 80% of their melting point, the atoms in the metal particles are getting activated, and they want to lose the energy, and they are starting making neck among the particles which are very nearby. Okay, so there could be some even some very small dislocations, which is giving you the chance of releasing the energy and transferring the atoms, and they are making a very small joints. So it is turned into very small necks, and these necks are growing and making a full component. Okay, so this is called as a first stage of centering, and this is called as a second stage of centering, and the final end when there is very small round pores. Okay, so it is a third stage centering. So in centering, it's very difficult to get 100% dense part. You can go maximum up to 99.99%. So there are a lot of factors like your particle size, okay, like your particle geometry, if it is spherical or not. Okay, there are a number of factors which is affecting the density of the material. Okay, so when we are dealing with the sintering and the 3D printed part, we need to see when we can get this third stage, because our optimum goal is to get high dense structure. So we can use different type of sintering processes. Okay, like there is a pressureless sintering, when you're just having a conventional tube sintering and you're just putting your sample here and you're heating up. Okay, there is no pressure on the there is no pressure on your sample, and there is some pressure assisted sintering. Okay, when you are putting pressure on the sample. Okay, and there is a electrical assisted sintering when you are putting a pressure and you are giving a potential of a DC power supply, which is giving very fast heating and large temperature at certain concentrated points. And there is a microwave sintering when you're having a microwave megatrons, which is generating microwave energy, and it is absorbed by the sample and it's heating from the center. It is going center to outside. The heat is going from center to outside. Here the heat is going from outside to inside. Okay. So if you see if you analyze this 3-4 sintering processes, so it is very difficult to use this pressure assisted sintering and electrical assisted sintering to make this this process which need the 3D printing and sintering. Okay, the question is why? Because when you are having a cylindrical samples, then it is fine, you can put load on this. But when you are having a complex shape, okay, like you are having a porous structure, it is hollow from inside, so you can't put load on this, otherwise it will destroy. You will destroy the sample, so you can't put load. Okay, so pressureless sintering or microwave pressureless sintering, here there is no pressure on sample, is the best suitable process to use it with 3D printing. So we have developed a new and a unique process, very cost effective. Just only within 2-3 lakhs you can make this setup. Okay, so this process, setup is combination of 3D printing and a combination of ultrasonic assisted pressureless sintering. So now you can see there is a new word game, ultrasonic. Okay, so I will explain why we need ultrasonic. Okay, so you can relate with the mechanism of sintering, you will understand there will be requirement of ultrasonic. Okay. So process works. So you need a CAD model. You can come up with any shape. Okay, this is a very complex form structure. This is a very complex form structure which is having a varying graded. Like you can see the strut size is varying, like it's a 1.2 mm to 1 mm or 0.8 mm at the end. So it's a graded structure. So you can make any CAD model. After CAD model, we will print it with any polymer 3D printing machine. So it can be FDM, it can be SLA. So in this case, I have used SLA because SLA is giving me very fine surface finish. So that's why I'm using SLA here. So then after that, the third step is to make a mold. Okay, so you can have your 3D printed sample. You can put it in a crucible, and you can put investing powder. You can use POP even with the water, or you can use any dental waste investment powder. Okay, you can just use it with some solvent, and when you mix it, it will be hardened and you will have a very hard structure here. And now in the pores, you having a investment powder. The fourth step is I will put this whole crucible in a simple open furnace. Very simple open furnace, which is around of 40,000. Okay, I can put it there and I can heat up. Okay, what will happen? Your polymer, which is of blue color, will burn out and you will get empty spaces. There will be empty space. Now this empty space, I will fill it with copper powder. Now here the condition. Okay, condition is your copper powder should be spherical in nature. If anyone want to answer me like why we need to use spherical, I will be really happy to hear that. So why we need a spherical particle? Why we can't have a irregular shape for centering? Anyone want to answer this?
Dear participant, anyone can answer.
Please to answer why we need why spherical particles is required for centering.
It's required for good densification.
So you can relate it with surface energy also.
Yes.
You're having a better surface area.
Surface,
okay. Yeah, you're having a better surface area and you're having a better connection. You can have better channels to lose the energy, to transfer the energy from one atom to other atom. Okay, that's why we need a spherical. So spherical powder, I am filling it here because I can't put a load. So I don't have any space to put a load. So these are free. I need a free particle. So I need a spherical particle. So now if I center a spherical particle, okay, so at the end it will give me a pore in the center. Okay, but then my sample will be only 70% center. I need my density around 99. Okay, to get 99, I need to put load here. I need to put load so that they can squeeze together during sintering. So let me give you one. Let me show you one example. Like this. So this is sintering. You can see that these blacks are the pores. Okay. So this is giving me only around, I think, 67 something percentage density. So I don't need it. I need these spherical pores, which is my final stage sintering. So it means my sample can't be extend. I can't extend my sintering process. So it has already reached nearby 99 or some 98%. Okay, 98.5, which I get it here. So I need to do some external. I need some external energy, which I can give it to the sintering particles, okay, at high temperature, so they can bond together. They can bond better. Diffusion could be better. Okay, so I can't put a load, but I can give some another external energy. So in this case, we have given ultrasonic vibrations. So we have tried to give vibration to this crucible so that vibration can reach my particles and they can bombard with each other. Okay, they can bombard with each other and they can create a local energy, local temperature, at very local joint points, and it can increase the densification. Okay, so we have designed this whole setup, which was only around 1.5 lakhs. Okay, so this is having very it's a simple setup, not a complex setup. It is having just a ultrasonic generator, and there is a ultrasonic horn, the big horn. So that was a new thing which we did. We designed a new ultrasonic horn, which is we are taking this horn up to 1000 degrees Celsius, and which is attached to this crucible when we are placed in this furnace. Okay, let me show you the actual picture. So this is the actual picture of the setup. Okay, so there is a horn. Okay, so and your ultrasonic generator, and to keep this transducer, which is converting our electrical energy into vibration energy, mechanical energy, to avoid keep this transducer away from the heat. So we have put a cooling system which is giving like it's having around 7 to I think 5 to 7 degrees Celsius temperature of water, which is continuously rotating through this horn, and your energy, your temperature is not raising here. We did a lot of simulation to see what could be the size of this cooling system, which could easily prevent the transducer from the heat. Okay. So this is the whole process, starting from the CAD model, and at the end, when you will sinter it with the with the ultrasonic assistant, you will get a dense structure, okay, which will be of having a same shape as CAD model. So these are some examples, very complex shape, very complex forms we did, and it is giving you very pure copper, which is around 99.9% pure copper, which is very difficult to get it with the laser-based system. Okay. So you can use it even for gold. Okay. Gold is also very difficult to make by laser-based system. So the major designing component is the ultrasonic horn. Okay, so I will not go in detail. Those know about the model analysis can easily pick up. Okay, so for generally when we are designing a ultrasonic horn for any ultrasonic machining, so we are using one nodal method, in which one we are having one node and we are having a two anti-nodes. Okay, so this is generally for the step horn, it is around 128 point something mm of the length by calculation, if you do the analytical calculations. But in this case, we need a very large horn. Okay, so we divide, we sum up these small horns into having 6 nodal points. Okay, and having a number of anti-nodes points, so that when we are starting giving vibration at certain amplitude, at the middle it should amplify, and the same amplification should go at the end. So this is our manufactured horn, which we manufactured, and we verify it with the vibrometer to check the vibration. Is it giving the same natural frequency, or it is giving the same amplitude value? Okay, so we required around 20 micron meter displacement in a longitudinal direction. Okay. So we have to do FEM modeling, like regarding model analysis, and have to check how much is the vibration is passing in a longitudinal direction. Okay, so what is the physics behind it? That is important to understand. So when I'm having a spherical particles, I'm giving a vibration. Okay, I have to move it in this particular direction. What will happen? So there will be rarefaction, there will be compression among the particles. Okay, so we have chosen random shapes, random size of the particle. Shape was spherical, but they were random shapes. Okay, particle size. So what was happening when we are giving vibration at the room temperature without putting any pressure? So these all small particles were tried to settle in the voids of larger particles. So by this, we have already increased the connection. Okay, this connection is generally in conventional process is done by pressing them to make a compact. Okay, so here we can't put pressure. So we did by ultrasonic vibration so that we can increase their connection. Second was when we are giving vibration, as I mentioned, there should be local heating by vibrating between them. So we did test and we find out there is around 35 degrees Celsius increase in the room temperature. Okay, from around 30 degrees Celsius, you can say it go up to 60 degrees Celsius at room temperature when we are putting vibration to these particles. And as we use it along with the centering, so the gap will be higher. Okay, so basically the densification at 950 degrees Celsius for the copper is around 99% as per the conventional centering, but we got at 850 degrees Celsius we got around 98%. Okay, so the reason getting at low temperature is you are having a local heating among the particles. Okay, So this is generally called as a flash heating. Okay, so we verify it with the mathematical model also. So what is happening when you are having a flash heat? Okay, the particle when they are bombarding, they are trying to create a dislocations, which we see by TM also. There are very small dislocations. Okay, you know dislocations are the defects. Okay, so it can be any screw dislocation or line dislocation. So through this dislocation, when you are having a chance of activating the atoms, so atoms are releasing their energy to make a bonds with another atoms which are free, which are in you can say in the terms of defect dislocation. So by having a flash heating, you are getting more dislocations and you are getting a better densification. So your material flow stress is decreasing when you are flowing the material from one particle to other particles. So that is the physics behind this fundamental behind this process. Okay. So I have shown you this example. Like we have got very good response of having we found spherical particles at lower temperature, and it is dense as compared to the conventional pressureless sinking process. Okay. So after developing this process, there are many concerns like, can we make it better? Okay. So only we added in the previous slide, we added ultrasonic vibration. So there are other factors in sintering like sintering temperature, heating rate, soaking time. Then number of things are there which could be optimized to get a better densified, better parameters which we use for densification. Okay. But in 3D printing, when you are comparing with CAD model, okay, so always our major requirement is the shape. We should get the same shape as our CAD model. It should be same shape. Okay. So for this, we need to optimize the shrinkage. Whatever with the shrinkage in X direction, Y direction, Z direction. Okay. So we need to avoid the shrinkage. We need to have a minimum shrinkage so that we should be nearby CAD model always. We can do some compensation. So we have approached some response surface methodology and find out some results and develop a mathematical model. This is your statistical model, okay, based on response surface methodology, and we come up with with the vibration was also the major factor which is increasing the density, but sinking temperature was also the major factor. So these two factors could combine to have a better densification, okay, which we found in interactions also. So ultrasonic power and sinking temperature, when they are combined, okay, so they are always giving you high density. Okay, so these are few results you can see without vibration. Okay, with the low temperature and vibration, you will find a lot of gaps. Yeah, but as the temperature is you're increasing, and also you're increasing the vibration, you are getting very closed, densified structures, okay, which is giving you better mechanical, electrical, conductive, thermal conductive properties. So we have tried to do some case studies with this. We have fabricated heat sinks. Okay, so in heat sinks, like during use for the heat transfer, you always need a good surface area. Okay, so that the heat can easily transfer among the two meats. Okay, so here we have chosen a lattice structure which is also having good surface area, and also in this lattice structure, in this struts, so we have kept temperature down. So you will see there is some porosity. Okay. So porosity was intentionally kept so that it can also have a heat transfer through this lattice structure, through these struts also. So you can have a double effect. You can have a micro effect also, and you can have a macro effect also. So both effects could be covered. So these are few other examples. Okay, so to test the efficacy, like can you make any complex shapes? So these are some complex shape we have made by this process, having the lattice structures. Okay, so you would see, like I have shown some mechanical properties where we are putting load, okay, in this direction and checking how the deformation is happening, like how they are getting densified. you will see these graphs are not much linear. Okay, you will say the density. If you having any ductile material, it should have a very linear, not much linear, but very smooth curves of compression testing. Okay, so but there are there are number of vibration irregularities are there. So it is due to the fracture of the studs. Okay, but the copper is ductile material; it should not fracture. Okay, so there is some still there is because the density is not 100%. There are micro porosities are there as I mentioned. Okay, so which is in the density. Okay, so which is giving the fracture when you're putting a load in a 90 degree. So your strut is like this, and you're putting a load at 90 degree. But when you're putting a load at when strut are sharing it at 45-degree angle, then it is getting smooth curves, which is giving you a ductile behavior. Okay. So now the art of this process is you're getting a design pores and you're getting some micro pores. So it can be really useful in a certain application where you need this type pores. Okay, you can't make by SLM. If you're having SLM, you make this shape with steel even. You make with steel even. So your strut will always having 100% density if the laser parameters are optimized. Like you have to example is you need a corrosion properties. Okay, like for iron, Fe, like using a biomedical implant, you need a local corrosion. So then these micropores are very helpful. Like there was a question in the previous talk why acoustic observations. For these small micropores will be helpful for acoustic observations. Okay, and these can be used for another type of like cell culturing. So you're having a design structure which is having a giving you systematic orientation of cell culturing, but the micropores will enhance the cell attachments. Okay, so this is giving you a number of advantages if you have to focus on one particular application. So after proving this concept, like we can make the part, so we can do different type of applications. We use it for different type of application. The challenge was like, can we use it for other materials? Okay, so we say let's test this for composites. Okay, can we make any graphene-based composite, CNT-based composite, graphite-based composite? So we choose copper plus graphene. Okay, copper plus graphene is not possible by using SLM. You can't make it by SLM. So this was the first attempt where we use 3D printing and the science sintering concept, because when you are having copper and graphene, we are mixing them, so you will destroy the sphericity of the particles. Okay, so you can't mix them properly for SLM. But here, when you are having vibration is at micron level. So you're having a micron length graphene, and you have nano thickness. Okay, so you can try to mix them properly so that it can adhere. Like you can see, graphene is on the spherical particles, graphene on the spherical particles. They can mix properly, and it can adhere on the spherical shape, and you can get a proper mixture of copper graphene. I will show you some pictures. Like this is we have mixed it, and you can see this picture. Then this is without ultrasonic vibration. So we have not given vibration. Okay, so you can see graphene is having a bunch. It's a bunch of graphene, which is not homogeneous mix. But when you are putting a vibration, it is properly packed between these spherical particles. Okay, so this is giving you better properties, like better electrical properties. Like we have tested it with for some tribological application on a pin on desk, and your ultrasonic assisted pressureless sintering will always give you better results as compared to the conventional process. Okay, so we have tried to make another forms, which is a copper graphene forms, and tested their mechanical properties, heat transfer, electrical conductivity. It can be useful for in even we are trying to do it for silver. Okay, where we can use it for some nuclear applications. So these are the examples I have shown you. Okay, so you are having a very uniform packing of graphene in the copper, and you can make any type of a copper graphene shapes. So this is not limited to any material. You can use combination of copper plus graphite, copper plus even nanoparticles of any other material, other metal. You can mix them. You can sinter it. You can even, it's very handy to publish articles. You can make number of articles from this type of process. Okay. So, but understanding of the physics is really important in this process. Okay, to how these things, how this process are working. Okay, developing some parts and for publication also is fine, but you must understand the physics behind it. Okay, to explore more things, we try to see the structure of the particles. Okay, like you're having a two particles. So this is a model given by Rockland. Like when you're having two particles, they are centered together. So you're having a diameter, the radius of A, and a cross-section, joint cross-section is X. You can try to see what type of physics is happening by this combination by X by raised to power N, and N is giving us say sinking rate component, and you are having a T is a temperature. Soaking time means you have kept this for certain time, temperature for certain time. This is soaking time. If you have these experimental values, you can find out rate constants. So from the rate constant, we can understand the physics of this type of process. Okay, so you can simply write this equation, this B, in the form of B naught and exponential of minus Q by RT. Is the harness equation we are using heat transfer, where your Q is activation energy. It depends upon the particle and particle size and your what is the particle material. Okay, so this is known for most of the material, and you're having a temperature, you're having universal gas constants. Okay, so for, as I mentioned, when we are doing ultrasonic centering, you are bombarding them, and we are saying we are having a generation of this temperature. Okay, for to verify this as per this model, okay, which is a well-known model in centering, we added a component delta T. So delta T, we are saying this is an increase in temperature. Okay, so this delta T we have given with some expression, which is expression given by Bhushan et al. Like when you are having two surfaces, you are trying to in a cyclic mode, you are trying to just rub them together. So you are having a increase in temperature, which is depending upon the amplitude of vibration, how much vibration is happening, time of vibration, up to what time we have done this, given this vibration, and what is the thermal diffusivity, okay, which is related to the thermal conductivity of which is of copper. What is the particle size? Okay, what is how much is the heat generated? Okay, that heat generation is depending upon coefficient of friction, ratio of amplitude vibration. So these all things can be calculated from experimental things, because we have a horn. In the horn, we know our what is the amplitude of the vibration, what is the time of how much time of vibration we will give to the particles at high temperature, what is the thermal conductivity of our particles, what is the shape of the particles, all things are known. So we added this component here, and we try to verify our X by A. Okay, so for the verification, we did SEM analysis on the very large particles. It is of 100 microns. We did taken 100 micron particles, and we did experiments, and we tried to calculate this one. This is our X, and this is our A. So we find out for different soaking times, the T, 60 second, 180 second, 300 second, 900 second, and at different temperatures, capital T. So we did it for at different temperatures, and we found the X by A relation with T time. So our mathematical relation was X by A, okay, and between T, so we just make it in a long log term, and we just plot it and get the constants. Okay. So the n, which I was saying, the n component, our n component. So n component, as per the literature, is giving us the mechanisms. Okay, what type of mechanisms are happening? So if you can find out the n value, then you can relate it with literature and can say the evaporation and condensation is happening, plastic flow is happening, grain boundary diffusion is happening. What type of mechanism is happening? So that can be related to understand the physics. So we found there is a n which is around these values from 5 to 6. Okay, so there is a combination of surface diffusion and the volume diffusion. Okay, so generally in sintering, the surface diffusion is happening, though the diffusion is happening in the sintering. But from the volume, so due to the having better dislocation, there could be chance of having better volume diffusion. Okay, so we are not going in the science of this diffusion mechanisms. Okay, but due to dislocation, there is a better chance of volume diffusion, which we verified with our experimental results. So also we did it for the number of experiments to see, is it giving us a uniform distribution, and are we getting the same universal distribution curve from the experiments which we are getting from our analytical calculations. So I want to thanks. I think I've taken 1 hour, so we can take questions if you are interested to ask me anything, please.
Yes, yes. Yes, Dr. Gurminda. Dear participant, yeah, please raise your hand or unmute and ask your questions that you're likely to ask.
Hello, sir.
Yeah. Yes.
Yeah, what should be the particle size for that copper spherical particles?
So it is perfect to have minimum as possible. If you can go with the nanoparticles, you can get a 100% density around 700 degrees Celsius even. So it's better to have a mixture of micron and nanoparticles when you're using this type of sintering, pressurized sintering. But better to have a minimum as possible, because it will take less time to sinter, and it can be sintered at low temperature also.
So is there any role of uniform particle size, or there should be some non-uniform particle size? Otherwise, if there is smaller particle size and bigger particle size, they will get accommodated somewhere in between.
Yes, that's why I was telling we are using vibrations, okay, so that the smaller particles can be easily packed between the packing of the large particles. Okay, that's why we are using ultrasonic vibration.
Okay, thank you, sir.
Yeah.
Okay, Anita Patki, yeah, you please proceed to ask your question as you have.
Yeah, good evening, sir. I
Yeah,
had a
good
question like, can we use this process for bronzes and like copper alloys, bronzes and brasses?
Yes. It can be used for any process. Can be used for any metal. It can be used for any ceramic.
Acha, because like porous bearings are manufactured by powder metallurgy. So if we
Yes,
use
you
this,
can make.
I think we'll get a good bonding characteristic or densification.
Definitely. So it can be used for any type of metal, any type of ceramic.
Okay, thank you. Thank you.
Yes.
Yeah, anyone? Yes, Dr. Nitin Pagar and
Sir, SC and BCC means what?
Sorry?
BCC, you.
Body
So that was a body-centered cubic structure. So it was a so it was a latex structure of. So we use a simple. Sorry.
Yeah. So copper is having a FCC cell structure. So
Yeah,
that
is a copper structure. The structure which I was using BCC, that was for the structure, not for copper particle.
So for sintering, so this metallographic study is affecting on this.
Metallography will not affect because I am not changing the copper structure. I think you're having some confusion here. Let me go back to my slide. So this one, this is a form structure. This BCC is for form structure. This is not for copper. It's a shape.
Printing structure, I
It's
think
a
so.
printing structure. You
Yeah.
can say printing structure is a shape, not the
Okay.
material. So I can't change the crystallinity structure of the material.
In such a structures, these BCC and such structures is morely prone to the interstitial spaces. That's why I'm asking.
Yeah,
Actually.
yes, you are right. Yes.
Yeah.
Okay, Dr. Ganesh Burika, sir, you
Yeah.
could please proceed
Hello.
with question. Yeah.
Sir, my question is related with earlier question.
Yes.
When the pattern cavity is obtained,
Yes.
so in that pattern cavity, how the lattice structure it is being obtained?
Yes.
Because when the
So
pattern is solid, then it is no issue. But
yes.
curiosity is how the lattice structure is obtained with the help of that.
Yes. So
With
let me
this,
show the schematic. You will understand better. Okay. So this is your lattice structure. Okay. So in this you can see this is a cross X. Okay. So this pore is filled by the investment powder itself. Okay. When you are putting investment powder in a solution which is in a liquid state, when you are pouring it, okay, it is getting solidified. So it will fill inside this the porosity of this lattice structure. Okay, so it will fill, and when you will have a when you have a free space, this will be free space. This space will be only of the lattice structure. This is like this.
yeah, it was in a liquid state, whatever that filling material.
No. Initially, this is when you are filling it. It's like a POP. We are
Yeah,
mixing the POP with the water. Okay, it is getting solidified. Okay, let's assume we have mixed with POP with water, and you have filled this whole crucible with POP water, and this liquid will go inside this pores. Okay,
yeah,
then it will solidify inside, even inside this pore. This liquid will solidify. Okay, then you can just burn this polymer inside the furnace out of about 200 degrees Celsius. So you will get this cavity, which is of form structure. Now the cavity will have a form structure. Okay, so you
yeah,
will put copper, and the copper particle will move like this. Okay, it will move uh, at this on the lattice structure. So it will look like this. Then you can
yes,
sinter it.
yeah. Got it, sir. Thank you.
Yes.
Okay, next question. Raise hand is from Shital Chavan. Please unmute your mic and ask the question.
Okay, sir. Good evening, sir.
Yes. Good evening.
Hello, sir. I am
Yeah, I
audible.
can hear you.
Yeah, you're audible.
Sir, what are the effects of vibrations or different frequencies on in terms of strength of that composites, or how you optimize that vibrational frequencies to give in during the ultrasonic vibrations?
So it's depend upon your setup. Like in our setup, we are having a transducer, okay, which was working at 20 kilohertz frequency.
Okay, sir. Suppose if I give the 50 kilohertz, 15 kilohertz, then what are the effects on the strength or in mechanical characterizations of that composite?
So we have not tested for 50 kilohertz, like we have tested for 20 kilohertz. So what will happen, I can tell you. So what will happen when you are having a higher frequency? Okay, so you'll have a better bombarding of the particles. Okay,
Yeah.
it will bombard with each other at a faster rate. Okay, so you will have a more chance of dislocations. You have a more chance of local heating. Okay, it could give you better density.
Okay, so like there is optimization techniques to set the good vibration frequency so to get good strength.
But these are very costly products. Getting a transducer, it's of
Yeah.
1.5 lakh. So you
Yeah.
can't, instead of making a whole transducer, we can optimize other parameters which are cheap and easy to do.
Yeah. Yes.
Yes.
Oh, okay, sir. Okay, thank you.
Yeah, Dr. Pritesh Bansor, please ask your question.
Yeah. Sir, how these lattice structures are, so it is made in the in solid model. How do we prepare the solid model of this lattice structure? Which software we can use for it?
I have made it in SolidWorks. Okay. So, but there are now these days, because these are very difficult to design in by manual way. So now these end topology is there. Even the academic license for 1 year is free. Okay, end topology you can use it. So we can make easily the structures by any type of graded structure, other structures. Now even you go to GitHub, okay, you will get simple code, Python code for the structures, LaTeX structures. You can get MATLAB code or a Python code for LaTeX structure, where people have given you have to choose what is the width, what is the thickness, what is the shape. Like you need a BCC and a simple cubic. What type of shapes are required? You can just fill it, and you can just compute it. You will get the shape. And then you can save it as a STL file.
Okay, sir. Thank you.
Dear participant, anyone have a questions? Please feel free to ask. Okay. So we are at the end of our session 2. So I hope there will no any more question from the participant. Okay. So, dear Dr. Gurminder Singh, on behalf of Department of Mechanical Engineering, Cummins College of Engineering for Women, Pune, and on behalf of our organizing team, I would like to very thank for your time and giving an insightful session on low cost additive manufacturing, specifically for metals. So I'm very much thankful to you for delivering a session and giving a more insightful learnings to our participant. So I'm very much thankful to you. Thank you very much. Even you have a very busy schedule of upcoming conference at IIT Bombay. I think it's on a couple of days. It's just left to start the conference. So even that you make possible to come and give a session to our participant. So on behalf on that particular note, I am very much thankful to you. The session was very informative. There are very good comments I'm able to see in the chat box. So, dear Dr. Gurminder Singh, thank you very much for your expert session delivery.
Thanks for calling me. It was very good interaction session. I will be really happy to come in person to have better interaction with all the mates and also with the students to see to understand the 3D printing in a more fundamental way. Okay, soon I will launch a CDP course also, so we can go to more fundamentals level, which is missing now these in literature. Okay, which is required at industrial level definitely. So,
yes.
Okay.
Yes.
Thanks everyone.
Yeah. Thank you. Bye. Thank you, Dr. Gurminder. Dear participants, we have come up to the end of our day 1. So